Hello, in this video we're going to discuss a topic called LOTUS, and that's an acronym for Law of the Unconscious Statistician. And it has something to do with taking the expected value of random variables and functions of random variables. So what I'm going to try to do is give my best intuitive feel for what's going on, and then kind of then prove it on a more theoretical basis. And so a little background is, if we look at the expected value of x, it says take each value of x times its respective probability of that x happening, summed over all values. Expected value of y is respectively, each value of y times the probability of y happening, summed over all possible values of y. That's the definition of expected value. But what if we let y equal the expected value of x, and on a test or a quiz, or if I asked to prove or show what the expected value of x squared was, we'd go the expected value of x squared times the probability of x happening, summed over all possible x, and that would be it. But why don't we think about it as, this is a random variable, and so values of that random variable are x squared. Why not have the probability mass function of x squared? Well, you don't need it, and that's kind of what the law of the unconscious statistician is. That if it's a function of x, and we want to take its expected value, we can just take the function of x times the probability of each x happening, summed over all possible values. And so we do that unconsciously, or at least that's the part of the title there. So a little more intuitive feel. If we have a random variable x that takes on positive values, and each has a probability of happening. This probability is 0 happening, probability 1, probability 2, 3, 4. And then this is the expected value. And if we take the expected value of x squared, so really we're taking each particular value times the probability of it happening, which is really just, this value here. So that's example 1. So example 2 is where these can be any variable or any value, and so x takes on integer values, and we're going to look at y equals x squared. So these only take on these values here. So to find the value of y, that says take each value of y times the probability of that y happening. So if we look at this one here, it takes on 0 with, and that probability 0. It takes on a 1 with the probability of P1 and P minus 1. So this combined probability is that. The probability it takes on a 4 is the probability that a 2 happens or a minus 2 happens. And we can keep doing that. A probability of a 9 is the sum of the probability of a 3 happens plus the probability of a minus 3 happens. And then we can keep going. But here we can distribute that number into each one of those. So here, it's the same. So it's 0 squared, and then 0 squared, or 1 squared times P1 minus 1 squared times P minus 1, and so, but this right here is just the expected value of x squared times the probability of each x happening. And so this is maybe a little more intuitive feel for why it happens. Now, to prove it more generically, let's let x be a random variable with probably mass function f of x. And if we let y be a random variable g of x, then the probably mass function of y. So what this says is, for a given y, the probability of it happening is you sum over all x's such that g of x is equal to y, and you sum all those probabilities, and that's the probability of y happening. So this is a little subset. Then, we're doing it for each particular y. We do this again. So we're breaking up y into like little pieces, of this. So if we look at the expected value of y, that's this, y times f of y. But f of y, we said, was for each y, we're going to sum over the x's such that g of x is equal to y, of the f of x. So this is equal to f of y. Well, we can take this y into this summation, but then if we do this for each y, and then we find the x's that go to that y, and then look at the next y, find the x's that go to that y. We do that for all y. That's the equivalent of just summing over all x's. And then we can plug in our g of x for y, and we already have f of x. Well, that's the expected value of g of x. And so that's a little more rigorous proof of why it happens. Now, from a continuous standpoint, I want to give a little background first, and let's look at the chain rule. So let's look at the derivative of x with respect to this composite function. So it's the derivative of the outer function with respect to g of x, and then the chain rule says we got to take the derivative of g with respect to x. So this is how we write it. But what if we let g be an inverse function of f? So g is minus f of x. So this composite function is x. And so if we take the derivative of x with respect to x, that's 1. So this right here is this side. And then we still have this over here. And then we can divide this piece to the other side, and we get this. The derivative of g is 1 over, f prime of g of x. But now let's rewrite g in terms of the inverse function. So really g, we said, was the inverse of x. So if we take the derivative of the inverse function, that's equal to 1 over f prime of f inverse of x. Okay, and we're going to borrow that little piece here in a second. So let's now switching topics. So we have y, which is a function of x, and we want to find the density for y. So what we do is we back solve for x. So that's g inverse of y. So f of y is equal to f of x, but we stick in this value for x and then times the Jacobian, which is the derivative of this with respect to y. Okay? But the derivative of an inverse function we just showed was this. Okay? So this right here is the density for y, for a random function of x. Or not a random function, but a function of x. Okay? So now let's look at this expected value. So the expected value of g of x, now the law of unconscious statistician says it's g of x, f of x, integrated over all possible values of x. But let's make a change of variable. Let's let y equal g of x. So that means back solving for x, it's equal to the g inverse of y. Take the derivatives of both sides, we get just dx, and here we get this 1 over g prime of g inverse of y, dy. So now we plug those values in. So for g of x, let's put y, and for that x, let's put this value, and then for d of x, let's put this. So we just make all our substitutions in, but this piece right here, we just said was the density for y. So we can just call that f of y. And so the expected value, you know, of y, which is g of x, you can think of it like this, but really the underneath is this. It's y times the density of y. Well, that's all I have for today. Hopefully you enjoyed that. I sure did. Please like the video if you did, and subscribe so you don't miss the next one. Thanks. Bye.